Right, as you can see, I'm abandoning question 2. In the interest of time, really. I don't want to waste more time thinking about that one. We may come back to that one. Question 4, wave motion, and I hope this is going to prove a little bit easier, at least for me. Acceleration due to gravity, 9.81 meters per second squared. Right, a cork floats on the surface of a pond across which a sinusoidal wave train of wavelength 10 meters and amplitude 0.2 meters is travelling. Good idea to draw a diagram. So we've got some waves, amplitude 0.2 meters, wavelength 10 meters, and a cork is floating. So what the cork is going to do is just bob up and down like that. So there's a sinusoidal wave train going through. The bob is going to be in simple harmonic motion. Okay, the velocity of the waves given by v squared equals g lambda over 2 pi plus 2 pi gamma over lambda rho, where rho is density, gamma is surface tension, and we're given values for those. Lambda, of course, is wavelength. Show that the equation is dimensionally consistent. So in other words, the units of that are going to be the same as units of that because that's a plus, and they're going to be the same as units of v squared. So let's do things in terms of dimensions. Now, when we talk about dimensions, a physicist would write the dimensions, say, of mass, and use angle brackets to mean dimensions, and abbreviate that by capital M. Length as capital L, and time as capital T in angle brackets. You could equally work with SI units. So what we have, and we've not got electrical currents flowing or anything like that, so MLT should cover this. So on the left-hand side, we have the dimensions of v squared. V is just a velocity, so it's length per unit time, meters per second squared. So length squared. Okay, right-hand side, we should get length squared time to the minus 2. First half, what are the dimensions of g? Lambda over 2 pi. Well, g is an acceleration, so that's a length per times squared, meters per second squared. Lambda is a length. 2 pi, of course, has no dimensions, it's just a number. So we've got L squared t to the minus 2. Same as left-hand side. That one's nice and easy. Right-hand side, second half. 2 pi gamma over lambda rho. Dimensions of that. 2 pi is obviously dimensionless, we'll just write dimensions of 1. Gamma, this is where we may have to do some thinking. Right, gamma has a tension, it's newtons per meter. We'll come back to that one. Lambda is a wavelength, so that's a length, and rho is density, so it's mass per length cubed. Kilograms per meter cubed. All we want to know is gamma 1. Let's go over here and work out gamma. I should say work out dimensions of gamma. Okay, newtons per metre are the units. Metre we know about, that's the length. What is a newton? Well, this is where you have to work through your fundamental equations. Newton, we can get that from force equals mass times acceleration. So that's a newton, the force one. So the dimensions of force is going to be the dimensions of mass, which is m, times the dimensions of acceleration, lt to the minus 2. So that's m lt to the minus 2. So dimensions of gamma, which is a force per metre, so that's your dimensions of force times L to the minus 1. So that's your dimensions of force mL t to the minus 2 times L to the minus 1. My L's go, so it's just m t to the minus 2. Let's just bring that in there. Hopefully this will work. Mt to the minus 2. M's go. L times L to the minus 3. That gives me L to the minus 2 on the bottom. Bring that up. L squared t to the minus 2. Same as others. Done. Happy. After question 2, that makes me happy. Part B, calculate the wave speed. You could of course use kilograms, meters, seconds.